This lecture is about generalization and discrimination and some of the experiments to investigate these phenomena found in both classical conditioning and instrumental conditioning. So just as a review, generalization, well, that's the degree to which two stimuli are perceived as being alike. So if I was to play a tone that's 500 hertz, and reinforce the animal, they would probably respond to a stimulus that's 450 hertz or 550 hertz because they're similar. Discrimination is the degree to which two stimuli are perceived as being different. So if an animal is trained on 500 hertz tone, they're going to hear the 450 hertz tone as different, and so they might not respond as much. The decline in a response because of discrimination, that's called a generalization decrement. So in auto shaping, we might train a bird with a yellow light. Yellow light is followed with reinforcement. And then we might test an orange light. Now this is a discrimination of color or a generalization of color or a purple light. And we might test them all and look to the degree that an animal responds to each of the colors after being trained on the yellow stimulus. And we get what's called a generalization gradient. This is the orderly relationship between the strength of the response and the generalized stimuli and the similarity of those stimuli to the original CS or S1. So in this case, train on the yellow light, we see the response will go down the further we get from that original color. This would be the same if this was tones. As we get away from the hertz in terms of the tone, we're going to get a decline in a response. So this might be a generalization gradient of responses after being trained on the yellow light. So there are many methods for investigating generalization gradients in different modalities with different animals. One is called the multi-stimulus procedure, and we condition a stimulus, let's say a 200 hertz tone. And then we have a nice high response to that 200 hertz tone, and then during extinction, in other words, we don't reinforce, we try out randomly a lot of different stimuli and look for the responses. This is often a within subject design, meaning that an animal is trained on one stimulus and then the same animal gets to respond to several. Another is called the single stimulus method, and we condition on an S+, and then we test a single stimulus during extinction. So trained on 200, let's say, and this single animal then is extinguished on 150, and we might look at responses and resistance to extinction. This is often a between subject design, meaning that each animal is trained on one and then given extinction on another. So finally, this one is called the maintained generalized procedure. And the animal is trained on one stimulus, let's say 200 hertz tone, and then it is tested on another stimulus along the gradient. So it gets 200 reinforced, and then we see what it does to 250. Then 200 reinforced, then we see what it does on 150 in terms of hertz or something like that. We keep coming back to reinforcing the S+, and then we test a lot of other stimuli to see their response levels. So this is a rather famous study. It's just on generalization. This is Gutman and Kalish in 1956. And these are the wavelengths of light. This was done with auto shaping, and this is the mean number of responses in 60 seconds. So here are the different colors, and if it was trained on 530, it peaks around there, and you can see the generalization gradient decline as we move away from that color. Here we are at 600, a 600 color, or 580. 580 is about a little green, and then we test some of these others, and you can see the generalization gradient. These are really good methods for investigating senses and perception in animals. So we might test the animal's ability to discriminate different tones, different colors, different patterns. But just like excitation is generalized, which is what we've just talked about, inhibition, the signal of non-reinforcement, that's generalized as well. So we can create gradients of generalized inhibition using the summation test. Remember the summation test from the first section? So this is A plus AB minus. This is creating a known inhibitor. A plus AB minus. This is called conditioned inhibition. Then we train X as a exciter, and then we see how B reduces the response to X. B is a signal of non-reinforcement, X is a signal of reinforcement, X is an exciter, and we then test. But instead of testing B, we test the inhibitory quality of stimuli that are similar to B. Generalization. Okay, this is a rather famous study that looks at generalized inhibition. This is done by Wiseman and Palmer way back in 1969. And what we have is we have a stimulus, a green stimulus, that is associated with reward. Peck the key and the animal gets food, right? So this is an instrumental design. Green is associated with food. However, if a green circle comes up and it has a perfectly vertical line, the animal gets nothing. And we go back and forth on this. Green reinforced, green vertical stripe not. Back and forth, conditioned inhibition. And then we test the animal's probability of pecking a key that is a stimulus that's similar but not the same. So that's pretty similar. That's not as similar as the original. So that's the original, that's the conditioned inhibitor. That is essentially B, the black stripe that's vertical. What does the animal do there? Well, it's still black, so there's generalization. It's still a line, so there's generalization. But it's not a vertical line, so there's a little discrimination. Test different lines. So one might expect that the responses would increase as it became more discriminated. Increased because the black line here is a signal of non-reinforcement. The green is a signal of reinforcement. So the further we get from the original inhibitor, one would expect to show an increase in response. In other words, they don't see a completely horizontal line as an inhibitor because it's not as similar. Here are the results. The number of responses over a course of a given amount of time is very high with just the green circle. That's baseline. When we show the line that is inhibitory, 0, it doesn't respond hardly at all. But as we move away from, we change the line degree, 30 degrees, 60 degrees, 90 degrees, the animal shows a more likelihood that it will respond. Meaning that 30 is close to 0 degrees, and so they see them as inhibitory. In fact, negative 30, they see them as very inhibitory. But as we make it more and more horizontal, the responses go up because the horizontal line is discriminated from the vertical line. The vertical line is inhibitory, but the horizontal line doesn't generalize. Oh, it does generalize a little bit. It doesn't go all the way up here. It's still a black line, but it's discriminated from the original vertical line. So let's go back over. So this is 0. And this might be 30, right? And this is 90. So 30, 60, 90. And we And we get this generalization gradient for inhibition. Let's look at a couple of other experiments that deal with generalization of both excitation and inhibition. The first one's called peak shift. That's the name of this experiment. And it's a discrimination between S plus and S minus. There are two stimuli presented. And these stimuli are similar or along the same modality. So this might be 500 hertz reinforced, 530 not reinforced. Or dark gray and a lighter gray not reinforced. These are typically done, one way of doing it is called successive discrimination. This is where one stimulus is only presented to an animal at a time. It doesn't compare the two in real time. It only sees one at a time. This is followed by looking at a generalization gradient along that modality. Here are the results of peak shift. The highest peak, the greatest response is not to S plus, not to the stimulus that was originally reinforced. The results are that the highest peak of response shifts away from the S plus in a direction opposite that of the S minus. I'm going to show you what that means. It's good to have the definition, but then we're going to see what that means. So, 1959, Hansen did an experiment where he reinforced 550 nanometers wavelength. That was the S plus. That's a green, right? That's a color green, a shade of green. But then different groups had the S minus as either 55, very close, 555, very similar green, or 560 was the S minus in another group, or 570 in a third group, or 590 in a fourth group. So S plus, every time 550 came on, reinforced. Every time 560 came on in this group, not reinforced. So this is what it might look like. These are only shown separately at a time. This one reinforced, then this one goes away, and then this one non-reinforced. This is done for many trials, and this is done with auto shaping. And here's kind of the wavelengths. So here are my circles down in here. Here are the wavelengths of light. Get an idea how it looks. And then we test them all. We test a whole range within this field here. Whole range. S plus, S minus, test a whole bunch. And where does the animal respond the most? To a stimulus that was never shown during training. It wasn't an S minus, it wasn't the S plus, it was a new one, 540. So the most response is to this one. Even though this one was reinforced and this one was not, we get a peak in response shifting away from the S plus in a direction opposite that of the S minus. That is a result. So here we have, for example, reinforced on 550. And this is a control group. It doesn't have anything else. Just reinforced 550. That's all. It's just a control group. It's not a peak shift group. And we get this generalization gradient that peaks up here at 550 and everything's good. But if we reinforce 550 and don't reinforce 560 and then do a full generalization gradient, we don't find the peak to be at 550. We find the highest response way over here at 540, even though the animal has never seen 540 during training. The question is, why aren't they responding to the one that they were trained on? Why are they responding the most to the one that they had never seen before? Why did we see a peak shift in response? S plus reinforced, S minus not reinforced, the peak responding is to 540. One theory to explain this kind of paradox was proposed by a guy named Spence, very famous learning theorist, and it's called the excitatory-inhibitory interaction theory. Some people just call it the absolute theory, and I'll tell you what I mean by absolute in a second. He says that the reason we get this shift is just excitation inhibition. That's all it is. Generalized excitation and generalized inhibition. So peak shift is caused by an overlapping gradient of excitation and an overlapping gradient of inhibition. What is producing the inhibition? Let's go back real quick. What gains inhibition? S minus. It's not reinforced by definition. What gains excitation? 550 by definition. But does 550 have any inhibition? It was only reinforced. Does it have any inhibition? It does. What? It does. It does because it looks so much like 560. So there's generalized inhibition from this one over to this one. And generalized excitation from this one over to this one, as well as this. And all we do is calculate performance as excitation, generalized, minus inhibition, which is generalized. It's a very simple formula of P equals E minus I. It just means performance is equal to excitation minus inhibition. Take both into account, and the one with the highest peak performance is one that is not the one that was trained. So I did some math here. I'm just making up numbers here to try to illustrate what I'm saying. So let's say here we are, 550, reinforced. 550 is reinforced. And we'll just say that the peak amount of excitation here is 10. Well, 540 has 9. Why? Because it's similar. And 530 has a 7. I'm just giving this a value of excitation. Why does 530 have excitation? The animal's never seen 530. It was only trained on 550 and 560. Well, because 530 looks a lot like 550, and there's generalized. Not as much as 540. And way out here at 500, well, that's a pretty different color. And so the excitation is really rather low. But 560 was never reinforced. It was presented to the animal and not reinforced. Here's 560, not reinforced. Trial after trial after trial. 550 reinforced, 560 not reinforced. But 560 has excitation because excitation generalizes. Now let's look at inhibition. The peak of inhibition has to be 560 because that's presented to the animal and it's not reinforced. 550 is, 560 is not, and that has lots of inhibition. But 550 has inhibition too, even though it was reinforced. Why? Because it looks like 560 and excitation generalizes and inhibition generalizes. And all you do is calculate. E minus I gives us P. P is performance. P is amount of pecking the keys, probability of pecking the keys, number of pecks per minute, whatever you want to record. P is performance. It's behavior. So 550, the only response is, the final p-value is 1. Let's go over here. 550. Oh, it has the most excitation, but it also has a lot of inhibition. So P equals 10 minus 6 is 4. Let's look at 540. 540 has the animal's never seen it in training, but it has a lot of excitation because it generalizes to 550. It has a little less inhibition than 550 because it has removed it from 560 a little bit. 9 minus 4 is 5. So what has the highest peak performance if we just take into account absolute numbers of excitation, absolute numbers of inhibition? It's not that the animal's comparing anything, it's just the brain is calculating. So we're left with this curve. This is just simply graphing this. Excitation generalization. And you can see that it peaks at 550. That's great. Excitation is the highest at the reinforced stimulus, makes sense. But it declines as we go away. 560 has the greatest inhibition, but that also declines. And if I then calculate performance here in black, you can see that 550 doesn't have the highest performance value when you take excitation minus inhibition. Excitation minus inhibition here causes that peak shift. This is the most parsimonious way of trying to understand this. It's not that the animal is thinking and comparing, I'm going to go to the one with the lighter green or something. It's just unconscious excitation inhibition. Absolute theory. Now, that didn't go over so well from a lot of theorists at the time. One I'd like to talk about is a guy named Wolfgang Köhler. And he's a German scientist. He did a lot of work with apes. He's one of the first cognitive psychologists. And he thought, I think there's more to it. I don't think these are these absolute excitation. Animals think and they compare. And so he ran an experiment called transposition. And unlike peak shift, transposition is often done with simultaneous discrimination, meaning both stimuli are shown at the same time. And it's similar to peak shift, other than the procedure. And he worked, like I said, with a number of different apes and tool use and all that stuff. But this experiment was done with chickens. And he said animals understand relationships, a very cognitive psychologist's way of looking at things. They understand relationships. So here's what he did. He had two boards, and they had different degrees of some stimulus. I used shade. I don't think he used shade. I think he may have used different sizes of circles. But I'm going to use shade here. And here's a darker shade and a lighter shade. Darker and lighter. And it's simply you train the animal that comes over here. He can get some food. Goes over to the dark gray pad. He gets some food. Goes over to the light one. There's food there, but he glued it. Köhler glued it to the board, this lighter shade. The animal couldn't eat it. And you get this training over and over. Eat here, can't eat there. Over and over. And the question is, what did the animal learn? Animal could have learned sort of excitation inhibition kind of a thing, or he could have learned a relationship. That's Köhler's theory. Relational learning. I go to the one that's grayer. So, this is how he tested it. He tested it with the original stimulus that provided the animal food. Let's go back here. This one provided the animal food, but he then made one that was even darker. And if the animal understood this really high concept of relationship, not go to this gray, that's the gray one is the one I want. It's go to the grayer of the two. If I see two things, I get food. I can get food from the grayer of the two. Because if you look at this one, that's the relationship. He gets food here. He doesn't get food here. So maybe he understands a concept of go to the one that's grayer. So in this case, where should the animal make a choice to try to get its food if it understood the relationship? Does it go to the one where it got food before? No. They actually, the little chickens, went to the grayer of the two boards. And Köhler was like, yeah, see? They understand relationships. And so this could be what Köhler called relational learning. This is the higher concept stuff. This is bringing up some ideas that are more declarative. I understand relationships. It's not just this unconscious P equals E minus I kind of stuff. This is, I understand the concept of relationship. Go to the darker. But then we ask, can Spence's theory, his absolute theory, his theory of P equals E minus I, can it account for the behavior? And if you look at excitation, generalization in green, and do a P equals E minus I, performance is excitation minus inhibition, the generalized inhibition from this lighter gray, then what we find is that even with that, you get this greater P value. Even transposition, even simultaneous transposition, still we don't need this higher level. Remember way back with Morgan's canon, the principle of parsimony? Don't make higher order assumptions when simple mechanisms can explain. There's nothing simpler than P equals E minus I. Relational learning is an assumption of greater complexity. And one of the evidence that it's still an absolute thing going on here is what's called the distance effect. Because when you do this experiment, this type of experiment, and you go way out here, a great distance from the original, then these overlapping generalization curves really would predict the lighter of the two. And what we find with a distance effect is we lose the transposition effect. In other words, if the concept that the little chicken learned is go to the grayer of the two, way out here, this is darker. Go to the darker of the two. This one is darker than this one. So the animal should go here, but they don't. They, in fact, are indifferent, or they might even go to this one. They might even go to the lighter of the two, which would be explained by the absolute theory. We don't like in learning theory to jump to these conclusions. That's the job of the cognitive psychologist, not the learning theorist. They want absolute, unconscious, simple mechanisms of excitation and inhibition. You need a lot to prove to them something else is going on here, some kind of conceptual learning. Go to the darker of the two things you see. That, for a learning theorist, is some really high cognitive powers. Finally, we get to an experiment that can't be explained by Spence's theory. Finally, we get to an experiment that can only be understood in terms of cognitive psychologists like Curler's idea of relationships. This was done with monkeys. It's called the intermediate size problem. So imagine, if you will, you have 9 stimuli of different sizes along a gradient. 9 is the largest, 1 is the smallest, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's how you start. And you give this monkey some training. 5 is reinforced, but 1 and 9 are not. They get a lot of training with this. If they pick 5, they get food. If they pick 1, they get nothing. If they pick 9, they get nothing. And by the way, this is done in a simultaneous discrimination. In other words, he sees all 3 stimuli at once. And he has to go and pick this one in order to get food. Don't pick this one. You pick this one, you get nothing. Pick this one, you get nothing. Pick 5, you get food. Okay? In other words, pick the middle. Pick the intermediate size. Then they're tested. Simultaneously tested on stimulus 4, 7, and 9. 4, 7, and 9. Now, we have conflicting predictions here. We have Spence's absolute theory, and we have Curler's relational learning theory. They're predicting different things. The absolute theory says 4 is where you need to go, because 4 is close to 5. It's closer to 5 than 7. 4 is also a far distance from 1. And 7 is pretty close to 9. And 7 is 1 full point away from 5. 4 should have the greatest excitation minus inhibition score. Should have the greatest performance. But Curler would say it's going to go to the middle one. He understood. The monkey understood. Well, if I see things, go to the one that's in the intermediate size. Rewarded on size 5, non-rewarded 1, 9. That's the procedure. It's tested on 4 and 7 and 9. That's the procedure. Absolute theory, P equals E minus I. Or relational learning, go to the middle one or go to the intermediate size one. That's why this is a good experiment, because it put those two things against each other. So let's look at this with the p-value. Here is the generalization gradient of 5. 5 was rewarded. Let's go back real quick. 5 is rewarded. And 4 has a really good p-value because it's a good distance from 1. so it doesn't have as much inhibitory generalization. And let's look at 7. 7 is further away from 5 than 4 is. And it's kind of close to 9, so it still has a little bit more inhibition. So in the black lines are representing a p-value. P equals E minus I. It's just simply this full length of green minus this length of red. This full length of green, excitatory generalization, minus this little bit of inhibition. So we make a very specific prediction on Spence. Animal should absolutely go to 4. Absolutely should choose 4. Where does the animal go? The animals go where they're going to go. So, where does it go? No, it doesn't go where it goes. It goes to 4. It goes to 7. It goes to 7. The intermediate size problem cannot be explained with the parsimonious theory by Spence. The absolute theory can't explain it. Only thing that can explain it is Curler's theory of relational learning. We have proof that we can go up in complexity in our assumptions of what the animals learn. So, just as a general idea about this, in simultaneous discrimination, both stimuli are presented at the same time. And this is like transposition, and this is like the intermediate size problems. And with these types of experiments, relational learning tends to do a pretty good job. Transposition, it kind of goes back and forth on how that's interpreted. But if they can see the stimuli all at once, it does afford the opportunity for relational learning, especially in the intermediate size problem. In successive discrimination, like peak shift, each stimulus is shown by itself, tends to produce results that are more consistent with the absolute theory, Spence's absolute theory.